In 1811, a skull was pulled from the cliffs along the English coast. Nobody had any idea what they were looking at. The jaws were lined with hundreds of teeth. The eye sockets were so large that scientists who examined them later concluded they had been built for hunting in near total darkness, deep below the surface of an ocean that no longer exists. Whatever this animal was, it had not simply lived in the sea. It had been designed for it, engineered over millions of years to dominate it. That skull was the first crack in a door that science has been pushing open ever since, because behind it was a world most people know almost nothing about. For more than 150 million years, before whales, before sharks as we know them, before anything resembling the ocean ecosystems alive today, the seas belonged to marine reptiles, not one lineage. Multiple, completely separate lineages, each returning to the ocean independently, each adapting so rapidly and so completely that within a few million years, some of them had abandoned land entirely, giving birth at sea, never touching ground again. Some grew larger than buses. Some developed hunting strategies with no modern equivalent. Some reached levels of ocean dominance that nothing alive today comes close to matching, and then they were gone. Not all at once, not cleanly. The collapse had already begun before the asteroid that ended the dinosaurs ever hit. Some lineages had already disappeared millions of years earlier, not from catastrophe, but from something subtler and in some ways more unsettling. How does a predator that spent over 150 million years perfecting itself for the ocean simply stop? What ended an empire that survived everything the planet threw at it for longer than the dinosaurs ever existed? Tonight, we trace how the deadliest predators the oceans had ever seen rose from a devastated world, ruled the seas for millions of years, and ultimately lost their throne. But before we start, let me know in the comments if you have any topic suggestions you would like me to cover in future videos. Now, let's go back to the beginning of the ancient oceans. Long before the oceans filled with giant eyes and paddle-shaped limbs, the planet moved through a silence so immense that even the rocks still carry traces of it. Around 252 million years ago, at the boundary between the Permian and Triassic periods, Earth endured the most severe mass extinction ever known. Nearly 96% of marine species disappeared. On land, roughly 70% of vertebrate species vanished alongside them. Coral reefs collapsed into empty stone. Forests thinned under poisoned skies. Entire branches of life, once ancient and widespread, ended quietly beneath ash, heat, and darkened water. The oceans that remained were strange places. Deep waters carried little oxygen, almost unable to support complex life. Carbon dioxide drifted through the atmosphere at concentrations far beyond anything seen in the modern world, trapping warmth across the supercontinent of Pangaea. Along its vast coastal margins, shallow epicontinental seas spread like warm inland lakes beneath a pale Triassic sun. Food chains had become brutally simple. Many ecological roles stood vacant, waiting for something new to step into them. In that emptiness, evolution accelerated. The ancestors of the great marine reptiles still walked on land then, moving through river valleys, tidal flats, and humid coastlines that bordered the recovering seas. Some belonged to lineages that would eventually produce ichthyosaurs, sleek hunters shaped by water into forms uncannily similar to tuna and dolphins. Others were early nothosaurs, long-bodied reptiles with flexible necks and spreading limbs, ancestors of the plesiosaurs that would later cross every ocean on Earth. Nearby lived thalattosaurs, smaller marine reptiles with elongated snouts and unusual jaws adapted for shoreline hunting among reefs and lagoons. None of them were dinosaurs. Their story unfolded beside the dinosaurs, not within them. Nor were they fish, despite the fins and streamlined silhouettes many later evolved. They were reptiles returning to the sea independently, each lineage solving the same ancient problem through different anatomical experiments. Over millions of years, lungs remained where gills never appeared, and air still had to be drawn from the surface beneath open sky. The Triassic world offered unusual freedom for those experiments. Competition remained low after the devastation of the Permian extinction, while prey populations recovered rapidly in the warm coastal waters surrounding Pangaea. Ammonoids multiplied through the shallows. Fish diversified into newly opened habitats. Crustaceans and shelled invertebrates spread across the seafloor in enormous numbers. For any animal capable of adapting to marine life, the oceans provided room almost without limit. This long history would unfold across three immense geological chapters. The Triassic period, from 252 to 201 million years ago, formed the beginning, a restless age of recovery and invention. The Jurassic, from 201 to 145 million years ago, became the Great Expansion when marine reptiles filled the seas in astonishing diversity. Then came the Cretaceous, stretching from 145 to 66 million years ago, the final act when new predators emerged beneath changing oceans and the old dynasties slowly began to fade. Far above those ancient waters, the continents still drifted in silence, carrying the future with them. Somewhere along the margins of the early Triassic seas, an animal slipped beneath the surface and never fully returned to land again. The moment itself is lost. No fossil preserves the first decisive swim. No skeleton records the gradual surrender of feet to fins. Yet by around 250 million years ago, almost immediately after the Great Extinction had emptied the oceans, Ichthyosaurs appeared in the fossil record, already moving with startling confidence through open water. Their arrival feels abrupt even now. In geological terms, they emerged almost overnight. Within roughly 2 million years, certain ichthyosaur species had become fully oceanic, their bodies transformed so completely that survival on land was no longer possible. Limbs narrowed into stiff hydrofoil flippers, the spine flexed side to side through the water. A vertical tail fluke developed at the rear of the body, generating thrust with the same hydrodynamic logic later discovered independently by tuna and dolphins across entirely separate branches of evolution. The skull lengthened into a narrow rostrum filled with interlocking teeth designed for seizing fast-moving prey beneath the surface. This convergence was not coincidence. Water imposes its own geometry upon large swimmers. Across millions of years, unrelated creatures encountering the same physical demands often arrive at remarkably similar forms, shaped less by ancestry than by the quiet mathematics of drag, lift, and momentum. The speed of the ichthyosaur transformation remains one of the most unusual evolutionary episodes in the vertebrate fossil record. Many major anatomical transitions unfold slowly across layered sequences of intermediate forms, but ichthyosaurs seem to enter the Triassic already accelerated beyond expectation. Their transitional ancestors remain elusive. Paleontologists continue searching through early Triassic rocks for shoreline reptiles with partially modified limbs or tails, yet the record still opens with animals that already belong to the sea. Part of the explanation may lie in the unusual conditions of the recovering planet. Ecological systems had been stripped bare after the end Permian collapse, leaving enormous marine habitats thinly occupied. In those simplified oceans, evolutionary pressure favored speed, experimentation, and expansion. A lineage capable of exploiting open water encountered little resistance. Niches existed everywhere, suspended empty beneath warm surface currents. The scale of this radiation becomes clearer in places where Triassic sediments accumulated undisturbed for millions of years. In the Guanling Formation of southern China, black limestone preserves entire communities of marine reptiles, fish, and cephalopods layered together in ancient seafloors. In the Bassano Formation along the border of Switzerland and Italy, delicate ichthyosaur skeletons lie compressed within dark shale, their vertebrae and ribs preserved with extraordinary completeness. These deposits reveal not isolated species, but flourishing ecosystems already crowded with specialized marine hunters. Among the most remarkable discoveries is Symbospondylus youngorum, described from Nevada in 2021. Living only about 3 million years after the first known ichthyosaurs appeared, it reached roughly 17 meters in length and weighed an estimated 45 tons, approaching the mass of modern sperm whales. Its existence suggests that gigantism emerged almost immediately once reptiles entered the marine realm, as though the recovering oceans had briefly removed the usual evolutionary limits on size. And still, the beginning remains obscured. The rocks preserve the expansion more clearly than the origin itself. Ichthyosaurs became so successful, so rapidly distributed across ancient seas, that the fragile traces of their earliest shoreline ancestors may have vanished long before stone had the chance to remember them. Far inland from any modern coastline, among the dry mountains and desert basins of Nevada, pale ribs once emerged from pale stone in long curved rows, as though the earth itself had remembered the outline of an ancient shoreline creature. When researchers excavated the site in the early 20th century, they uncovered dozens of enormous ichthyosaurs resting together within the same layer of rock. Their bodies had settled there over 200 million years earlier, deep within a Triassic sea that no longer exists. The species became known as Shonosaurus popularis, and the graveyard surrounding it remains one of paleontology's quiet mysteries. Some skeletons lay nearly complete, stretched through the sediment as if lowered gently into still water. No clear signs of violent predation appeared on the bones. The animals may have stranded together along a shallow coast. They may have suffocated during a bloom of toxic microorganisms that drained oxygen from the sea. Some researchers have even proposed a breeding aggregation similar to the gathering behavior of certain modern whales. The stone offers possibilities, never certainty. By the late Triassic, ichthyosaurs had reached dimensions almost difficult to visualize within the recovering ecosystems of their age. In British Columbia, fragmentary remains discovered in 1991 revealed Shonosaurus sickaniensis, estimated at around 21 meters long. Even conservative calculations place its weight between 30 and 35 tons, making it the largest marine reptile ever confirmed from the fossil record. A creature of that scale required immense quantities of food moving continuously through the surrounding ocean. Giant cephalopods likely formed part of its diet, along with fish and perhaps smaller marine reptiles drifting through the upper water column. Gigantism emerged repeatedly during this period, not only among ichthyosaurs, but across multiple animal groups inhabiting the Triassic world. Warm global temperatures accelerated metabolism and extended productive coastal habitats across broad equatorial regions. Nutrient-rich seas supported dense populations of prey animals, while the ecological aftermath of the Permian collapse still left many competitive barriers unusually low. In such conditions, enormous size became less of a burden and more of an advantage. allowing large swimmers to travel efficiently through open water while conserving energy across vast distances. The geography of these ancient oceans survives now through scattered fossil discoveries across distant continents. In what is presently the Himalayas, researchers identified Himalayasaurus tibetensis, another giant ichthyosaur preserved within marine rocks, lifted thousands of meters above sea level by the later collision of India and Asia. The bones formed originally beneath the waters of the Tethys Sea, a tropical ocean that once separated the northern and southern halves of the world. Elsewhere, Triassic Ichthyosaur remains appear along the margins of Panthalassa, the immense global ocean surrounding Pangaea. Their distribution traces warm coastal currents that wrapped around the supercontinent in broad equatorial bands. These were not polar hunters or deep ocean wanderers yet. Most lived within shallow marine systems, where sunlight still reached the seafloor and prey gathered in abundance. Other reptiles shared those waters. Early placodonts searched lagoon bottoms with crushing teeth adapted for shellfish. Nothosaurs moved through estuaries and inland channels with long, flexible bodies built for ambush. The marine ecosystems remained incomplete, still carrying gaps left behind by the Great Extinction earlier in the Triassic. Yet within that unfinished world, giants already crossed the seas in slow arcs beneath the surface, immense shadows moving through water that had only recently begun to live again. Along the quiet floors of Triassic lagoons, where fine carbonate sediment settled through warm water like drifting dust, another kind of marine reptile moved with very different intentions. These animals did not pursue prey through open currents or cross broad distances with streamlined bodies. Placodonts belong to a separate branch of reptilian evolution entirely, appearing around 247 million years ago and developing one of the most unusual anatomies the ancient seas would ever produce. Their skulls carried broad, flattened teeth arranged like stone paving. Instead of piercing flesh, these teeth crushed. Placodonts fed close to the seabed, prying shellfish from submerged surfaces and grinding through mollusks, brachiopods, and crustaceans with slow mechanical force. In some species, the front teeth projected outward like chisels suited for levering prey loose from reefs and tidal rocks, before the rear jaws reduced shells into fragments. The rhythm of their lives seems to have matched the enclosed waters they inhabited. Most placodont fossils come from the margins of the Tethys Sea, preserved within sediments formed in shallow tropical lagoons stretching across what are now the Alps, parts of the Middle East and southern Europe. These coastlines were protected environments, rich in shelled invertebrates and seagrasses, where sunlight reached the bottom through calm green water. Over time, some placodonts became heavily armored. The most striking example was Henodus keliops, a reptile so unusual that its silhouette resembled a turtle nearly 100 million years before true turtles appeared. Its back carried a broad shell formed from interlocking osteoderms, dense bony plates embedded within the skin. The skull flattened into a squared shape, with narrow jaws adapted for selective feeding along the sediment surface. Rather than active pursuit, Henodus likely sifted and cropped soft organisms from the lagoon floor with slow, deliberate movements. Another placodont, Psephoderma alpinum, developed a similarly armored form during the late Triassic. Early paleontologists initially struggled to interpret its anatomy because the resemblance to modern sea turtles appeared so strong, yet the similarity emerged independently. Placodonts and turtles belong to different evolutionary lineages, separated by deep anatomical differences beneath the shell itself. Their convergence reflected the demands of the same environment, where stability, protection, and low swimming energy favored broad bodies and reinforced armor. These reptiles reveal how many ecological possibilities remained open during the Triassic recovery. Marine life was not rebuilding along a single path. Some lineages became swift visual predators, others drifted toward massive body size. Placodonts occupied another niche entirely, transforming themselves into durable bottom feeders, protected against predation by layers of bone and heavy torsos difficult to overturn or swallow. Their world, however, remained geographically narrow. Unlike later marine reptiles that spread across global oceans, Placodonts rarely ventured beyond the shallow tropical margins of the Tethys. Their dependence on calm coastal habitats may ultimately have limited their resilience as planetary conditions changed toward the end of the Triassic. Around 201 million years ago, during the extinction event marking the boundary between the Triassic and Jurassic periods, Placodonts disappeared completely. No descendants carried their armor forward into later seas. The lagoons that preserved their shells gradually closed beneath shifting climates and volcanic upheaval, leaving behind only flattened skeletons pressed into limestone, quiet remnants of an evolutionary experiment that existed for a brief interval and never appeared again. Across the closing stretch of the Triassic, the crust of the planet began to open. Deep fractures spread through the supercontinent as Pangaea slowly strained apart, and from those fractures came eruptions on a scale difficult to imagine in human terms. Lava flooded outward repeatedly for hundreds of thousands of years, pouring across valleys and lowlands until enormous regions disappeared beneath basalt. This volcanic system, now called the Central Atlantic Magmatic Province, eventually covered more than 11 million square kilometers, an area larger than the combined landmass of the United States, Canada, and Mexico. The atmosphere changed with it. Carbon dioxide accumulated in extraordinary quantities, warming the climate and disrupting ocean chemistry. Sulfur dioxide entered the air as well, producing intervals of cooling and acid rain that followed periods of intense heat. In the seas, acidity increased while oxygen levels shifted unpredictably through the water column. Marine ecosystems that had spent millions of years rebuilding after the Permian catastrophe entered another prolonged period of instability. Around 201.3 million years ago, the Triassic period ended within this turbulence. An estimated 76% of all species on Earth disappeared, making the event the fourth largest mass extinction in the geological record. The losses were uneven, selective, and strangely patterned. Some groups vanished almost completely, while others endured and quietly expanded into the spaces left behind. Placodonts disappeared entirely from the fossil record. Their specialized lagoon habitats and shell-crushing lifestyles may have left them vulnerable as coastlines shifted and marine chemistry destabilized. Thetanosaurs, another early marine reptile lineage, also vanished during the crisis. Most nothosaurs faded away as well, their long history in shallow coastal systems ending before the Jurassic began. Many of the giant Triassic ichthyosaurs disappeared alongside them, including the immense forms that had dominated warm equatorial seas. Yet extinction rarely moves with perfect symmetry. Certain ichthyosaur lineages survived the boundary and passed into the Jurassic, though often in reduced diversity and altered forms. More importantly, a branch of nothosaur relatives called pistosauroids endured through the environmental collapse. These reptiles still retained elongated necks and broad aquatic limbs, anatomical foundations that would later give rise to the plesiosaurs. Why some groups survived while others failed remains an active area of research. Geographic range appears to have mattered. Species distributed across multiple marine environments may have been buffered against regional collapse. Dietary flexibility likely played a role as well, especially during periods when food webs fragmented and prey populations shifted rapidly. Body size may have influenced resilience, since enormous marine reptiles required stable access to large quantities of food in ecosystems already under stress. Habitat depth may also have offered partial protection, with some marine environments remaining more chemically stable than others during the volcanic upheaval. When the eruptions finally subsided, the oceans that emerged were no longer truly Triassic. Coastlines had changed shape. Ecological roles stood open again, though not in the same arrangement as before. The surviving marine reptiles entered a reorganized world where familiar competitors had vanished and entirely new evolutionary possibilities had begun to appear. The Jurassic seas inherited the bones of the older world, but their structure belonged to something different now. The first great transfer of dominance among marine reptiles had already taken place beneath the surface, slowly and without ceremony, carried forward by whichever lineages managed to remain alive long enough for the water to settle again. In the stone quarries of southern Germany, there are slabs of black shale so finely layered that even the outline of skin can remain visible after 180 million years. Fish scales glimmer faintly across their surfaces. Delicate squid hooks rest beside vertebrae no larger than coins. Entire marine animals appear suspended inside the rock with such clarity that the Jurassic Ocean seems less extinct than momentarily paused. These deposits, known as the Posidonia Shale, formed beneath an ancient seafloor where oxygen was almost absent. Without scavengers or bacterial decay to disturb the bodies drifting downward, soft tissues endured long enough to become impressions within the sediment itself. The shale preserves not only skeletons, but shadows of flesh, stomach contents, embryos, and the contours of fins that vanished long before human beings existed to observe them. By the early Jurassic, the Ichthyosaurs moving through these waters differed profoundly from the colossal forms that had dominated the late Triassic. The extinction at the boundary between the periods had reshaped the lineage. The survivors tended towards smaller, faster bodies adapted for pursuit rather than sheer scale. Their skulls narrowed into more efficient hunting profiles, and their proportions became increasingly specialized for speed and maneuverability within complex marine ecosystems. Among the most abundant was Ichthyosaurus communis, preserved in extraordinary numbers along the Jurassic coast of England. Thousands of specimens from Somerset and nearby cliffs reveal nearly every stage of its life cycle. Some fossils retain traces of soft tissue around the flippers and tail. Others preserve stomach contents still compacted within the rib cage. A few contain embryos curled inside the body cavity, silent records of reproduction beneath the sea. Another species, Stenopterygius quadricissus, carried a feature that changed scientific understanding of ichthyosaur anatomy entirely. Several Posidonia specimens preserved dark carbon films extending above the spine, revealing the outline of a dorsal fin. No bones supported this structure. Earlier paleontologists had only inferred its existence indirectly from hydrodynamic logic, but the shale confirmed that ichthyosaurs possessed stabilizing fins much like those of modern fast-swimming fish and dolphins. Some Jurassic species became increasingly specialized for deep water. Ophthalmosaurus eisenicus developed eyes reaching roughly 23 centimeters in diameter, proportionally larger than those of any known vertebrate. Massive, bony rings reinforced the eyeballs against pressure changes during deep dives. These animals likely hunted within the dim twilight zone several hundred meters below the surface, where sunlight faded into blue darkness and cephalopods drifted through colder layers of the ocean. The stomach regions of Jurassic ichthyosaurs preserve fragments of those hunts. Fossils contain fish, vertebrae, belemnite guards, and clusters of hook-bearing tentacles from squid-like cephalopods. In some specimens, the bones belong to smaller ichthyosaurs themselves, evidence of competition or occasional cannibalism within crowded marine food webs. Reproduction had also become fully marine. Multiple fossils show mothers carrying unborn young, aligned, tail first, inside the birth canal, the same orientation seen in modern dolphins. Delivering the tail first reduced the risk of drowning during birth beneath open water. One famous specimen appears to preserve the final moments of labor itself. A juvenile halfway emerged from the mother's body when both settled into the sediment together. The Jurassic Ichthyosaurs no longer resembled pioneers testing an unfamiliar habitat. Their bodies had become entirely fluent in the language of the sea, refined through millions of years into forms capable of crossing depths and currents with effortless precision. There are moments in paleontology when a skeleton appears so unfamiliar that it seems assembled from mismatched animals. A compact body, 4 broad flippers, a neck extending outward in impossible length, ending in a small, narrow head filled with interlocking teeth. Early reconstructions of plesiosaurs carried an almost dreamlike quality because no living vertebrate moved through water in quite the same way. The lineage emerged from pistosauroids near the beginning of the Jurassic, around 200 million years ago, and endured until the final days of the Cretaceous. Across roughly 135 million years, plesiosaurs spread through every major ocean on Earth, adapting into forms that ranged from delicate, long-necked hunters to massive predators with skulls large enough to engulf prey whole. 2 major body plans gradually defined the group. The plesiosauromorphs carried elongated necks and relatively small heads, their proportions becoming increasingly extreme in some species. The pliosauromorphs evolved in the opposite direction, shortening the neck while enlarging the skull into a heavily muscled weapon designed for forceful bites and active pursuit. Among the most extraordinary was Elasmosaurid platyurus. Described in 1868 during the turbulent early years of American vertebrate paleontology, its neck contained 72 cervical vertebrae and stretched approximately 7 meters long, longer than the rest of the body combined. The anatomy confused even experienced researchers. Edward Drinker Cope, working from incomplete understanding, accidentally placed the skull at the tail end during his first reconstruction. His rival Othniel Charles Marsh publicly corrected the error, an embarrassment that helped ignite the long scientific feud later known as the Bone Wars. For many decades, plesiosaurs were imagined sweeping their necks side to side through schools of fish like serpents underwater. More recent biomechanical studies suggest a different picture. The vertebrae of the neck limited flexibility more than earlier reconstructions assumed. Instead of broad coiling movements, the neck likely functioned as a controlled strike arm, allowing the small head to dart rapidly toward prey, while the larger body remained relatively stable at a distance. Their method of swimming was equally unusual. Plesiosaurs remain the only known vertebrates to evolve a fully 4-flipper underwater flight system. Each limb moved like a submerged wing, generating lift rather than relying entirely on side-to-side undulation. Computer modeling and robotic simulations suggest the front and rear flippers probably operated in alternating figure-8 motions, producing smooth propulsion through the water with remarkable maneuverability. At the opposite end of the lineage stood giant pliosaurs, such as Pliosaurus funki, discovered in the Arctic deposits of Svalbard and formally described in 2012. Nicknamed Predator X in the popular press, its skull alone measured around 2 meters long. Bite force estimates approach 33,000 newtons, placing it among the most powerful predators ever calculated. The jaws carried thick conical teeth capable of gripping large, struggling prey without fracturing under stress. Plesiosaur fossils now appear on every continent, including Antarctica, where fragments emerge from rocks deposited when polar regions supported comparatively mild marine environments. Their global distribution reflects a lineage completely adapted to oceanic existence, crossing vast distances through seas that changed continuously across millions of years. In shape and movement, plesiosaurs remained unlike anything before or after them, their bodies following an evolutionary direction that the vertebrate world explored only once. Few marine reptiles have drifted so far from their fossil evidence as Liopleurodon ferox. In museums and scientific papers, it exists as a formidable Jurassic pliosaur, broad-skulled and muscular, built for rapid acceleration and violent predation. In popular culture, however, it became something far larger, transformed into an almost mythical leviathan whose dimensions expanded far beyond what the bones themselves support. The real animal lived during the Middle Jurassic, around 165 million years ago, in the seas covering parts of what are now England, France, and Germany. Fossil remains reveal a predator with a skull exceeding 1.5 meters in length, lined with thick, conical teeth suited for gripping, struggling prey. Conservative body estimates place most known specimens between 6 and 7 meters long, large enough to dominate many marine ecosystems of the period without approaching impossible extremes. That distinction blurred dramatically in 1999 when the BBC documentary Walking with Dinosaurs portrayed Liopleurodon as a 25-meter giant with a bite force supposedly 8 times stronger than that of Tyrannosaurus Rex. The sequence became iconic almost immediately. Viewers watched an immense pliosaur moving through darkened water like a living submarine, and for many people, the fictional scale fused permanently with the actual animal. The problem was not the existence of artistic interpretation itself. Paleontology often relies on reconstruction, especially when fossils remain incomplete. The issue lay in how rapidly speculation hardened into accepted public memory. No fossil material has ever supported a 25-meter Liopleurodon. The largest reliably confirmed specimen measures closer to 6.4 meters in total length. Even at that size, it remained an apex predator fully capable of hunting large fish and marine reptiles within Jurassic seas. Exaggeration can obscure something quieter but more interesting. The authentic animals already stretched the upper limits of predatory adaptation for their time. Massive jaw muscles anchored against reinforced skulls. Large paddle-shaped limbs generated sudden bursts of acceleration. Wide chests housed lungs capable of supporting extended dives. Their anatomy reflects millions of years of evolutionary refinement, not cinematic inflation. Other pliosaurs reached greater sizes with stronger evidence behind them. Kronosaurus queenslandicus, discovered in Queensland, Australia, likely measured between 9 and 10 meters long. Its skull alone approached 2.7 meters, among the largest predator skulls known from any marine vertebrate. Unlike the speculative dimensions assigned to Liopleurodon, these estimates rest upon more substantial fossil material, allowing researchers greater confidence when reconstructing body proportions. Even now, uncertainty remains part of the science. In 2023, researchers announced fragmentary Pliosaur remains from Dorset in southern England, sometimes referred to informally as the Westbury giant. The preserved jaw sections suggest a predator potentially exceeding 14 meters in length, though the material remains incomplete and active study continues. Such discoveries illustrate both the excitement and restraint required in paleontology. Bones rarely arrive as complete animals. More often, they appear as scattered fragments shaped by pressure, erosion, and geological time. Estimating total size from partial remains demands scaling methods that carry unavoidable margins of error. A larger jaw does not always indicate a proportionally larger body, and anatomical variation between species complicates direct comparison. Public fascination tends to reward certainty and enormity, while scientific practice moves more carefully through probability and revision. In the end, the tension surrounding Pliosaur reveals less about one predator than about the relationship between imagination and evidence. Ancient oceans invite speculation naturally, yet the fossils remain most powerful when allowed to speak within the limits of what stone can genuinely preserve. Along the margins of Jurassic coastlines, where tidal channels braided through limestone islands and shallow reefs, another lineage of reptiles began altering itself for life in salt water. Their ancestors belonged to the Archosaurs, the vast reptilian group that also produced dinosaurs, pterosaurs, and modern crocodilians. Yet over millions of years, these particular reptiles drifted farther from the familiar crocodile form until some scarcely resembled river hunters at all. They are known collectively as the Latasuchians, marine-adapted archosaurs that lived between roughly 190 and 145 million years ago. Their evolution unfolded along two broad pathways. The teleosauroids remained tied to coastlines and estuaries, carrying elongated jaws and low bodies reminiscent of modern gharials. They likely hunted fish in shallow marine environments, moving between river mouths, lagoons, and protected bays. The second branch, the metriorhynchids, abandoned nearly every limitation of their terrestrial ancestry. In these animals, the limbs transformed into paddle-like flippers unsuitable for walking on land. The tail developed a downward curving lobe supported by vertebrae bent into a shark-like profile, generating propulsion through lateral movement of the rear body. Fossils preserve evidence for salt-excreting glands near the eyes, physiological adaptations allowing them to process seawater while living far from freshwater sources. Some exceptionally preserved specimens even suggest the skin lacked the heavy armor and scales associated with modern crocodilians, replacing them with smoother tissue that reduced drag during sustained swimming. The extent of this transformation becomes especially clear in fossils from the Solnhofen limestone of Germany, a late Jurassic deposit famous for preserving delicate organisms in remarkable detail. The same quiet lagoons that captured the feather impressions of Archaeopteryx also preserved marine reptiles with traces of soft anatomy rarely retained elsewhere. Within those pale limestone layers lies Geosaurus giganteus, a metriorhynchid whose body proportions reveal an animal fully committed to pelagic life. Among the most unusual was Dacosaurus maximus. Unlike the narrow-snouted fish specialists surrounding it, Dacosaurus evolved a deep, compressed skull with serrated teeth more reminiscent of terrestrial predatory dinosaurs than crocodilians. Its head carried a blunt, muscular profile, capable of handling large, struggling prey. When South American material was described in 2006, newspapers nicknamed it Godzilla, though the actual animal moved not through cities but through warm Jurassic seas filled with fish. cephalopods, and other marine reptiles. What makes the meteorrhynchids remarkable is not simply that crocodile relatives entered the ocean, but how completely they altered their anatomy once they arrived there. Most marine reptiles retained at least traces of their terrestrial foundations in posture or locomotion. Metriorhynchids, by contrast, reshaped nearly every visible feature connected to life on land. They became streamlined open-water predators through one of the most extreme morphological departures known anywhere within the Archosaur lineage. Then, near the boundary between the Jurassic and Cretaceous periods, around 145 million years ago, the fully marine meteorrhynchids disappeared. Their extinction remains difficult to explain with certainty. Oceanic conditions shifted during this interval, and marine ecosystems reorganized once again, but the fossil record offers no single, clear cause. Some teleosauroid relatives survived longer into the Cretaceous, lingering near coastlines after their oceanic cousins had vanished. For a brief interval of geological time, crocodilian evolution moved toward the open sea with astonishing commitment, almost completing a transition that later generations would remember only through stone. For much of modern scientific history, marine reptiles were imagined as enlarged versions of living lizards, dependent on external warmth and slowed by cold water, in the same way a modern reptile becomes sluggish at night. The assumption seemed reasonable at first glance. They possessed scales, laid within the reptilian branch of the vertebrate tree, and lived long before mammals came to dominate the oceans. Yet over the past 2 decades, the fossils themselves have begun quietly resisting that interpretation. The change began not with dramatic skeletons, but with microscopic structures hidden inside bone. In 2016, a study led by Gilles Moulet and colleagues examined preserved collagen patterns within Ichthyosaur and Plesiosaur fossils. The internal organization resembled the tissues of animals capable of maintaining elevated and stable body temperatures rather than those whose metabolism fluctuated entirely with surrounding conditions. The results suggested some marine reptiles may have possessed regional endothermy, warming specific tissues, or perhaps full body temperature regulation approaching that of modern marine mammals. Additional clues emerged from exceptionally preserved soft tissue. Certain Stenopterygius specimens retain a distinct lipid-rich layer between skin and muscle, comparable in structure to the insulating blubber of dolphins and whales. Such tissue would have reduced heat loss while swimming through colder water, especially during deep dives where sunlight no longer warmed the upper ocean. Insulation of this kind carries energetic cost, but it allows sustained activity in environments that would otherwise drain body heat rapidly. Even the color of some ichthyosaurs has begun to reappear through chemistry preserved at microscopic scale. In 2017, researchers analyzing fossil skin identified melanosomes, pigment-containing structures, still arranged within the tissue after millions of years. The pattern revealed dark coloration across the back and lighter coloration beneath, a form of camouflage known as countershading. Today, the same arrangement appears repeatedly among open-water swimmers, such as sharks, tuna, and dolphins, reducing visibility from both above and below within dim marine light. If marine reptiles maintained elevated body temperatures, the ecological implications become profound. Warm muscles contract more efficiently and recover more rapidly after exertion. Sustained swimming speeds increase. Activity becomes possible in colder latitudes and deeper water layers where ectothermic animals struggle to function continuously. Large eyes and deep-diving adaptations in some ichthyosaurs fit naturally within this framework, suggesting predators capable of pursuing prey through environments inaccessible to slower, cold-blooded hunters. Bone growth patterns add another layer to the picture. Thin cross-sections of Ichthyosaur, long bones, reveal rapid juvenile growth rates marked by closely packed vascular canals and developmental rings, more comparable to modern marine mammals than to living reptiles. Some species appear to have reached maturity quickly, demanding substantial and continuous food intake to sustain accelerated metabolism. Still, the debate remains unresolved in important ways. Marine reptiles encompassed many distinct lineages across more than 150 million years. Physiological strategies may not have been identical between ichthyosaurs, plesiosaurs, mosasaurs, and marine crocodilians. Some researchers argue for fully endothermic metabolisms in particular groups, while others favor intermediate conditions combining reptilian ancestry with partial heat regulation. The uncertainty itself reflects the unusual nature of these animals. They occupied ecological roles that pushed the reptile body toward solutions rarely attempted before or since. Beneath their skin, metabolism may have become as specialized as their fins, eyes, and skeletons, shaped gradually by cold currents, deep water, and the immense energetic demands of life far from shore. By the middle of the Cretaceous, the oceans already carried a long memory of reptilian rulers. Ichthyosaurs had crossed the seas for immense stretches of geological time. Plesiosaurs had diversified into hunters of many forms and sizes. The marine world seemed ancient and established, its major lineages settled into place through millions of years of adaptation. Then, comparatively late in the story, another group appeared with startling speed. Their ancestors were not streamlined pelagic specialists or long-necked marine wanderers. They belonged instead to the squamate lineage, close relatives of monitor lizards and snakes. Mosasaurs began as terrestrial reptiles, whose bodies still carried the proportions of land predators, muscular tails trailing behind clawed limbs, suited for movement across shorelines and shallow estuaries. The fossil record first reveals them around 98 million years ago. In evolutionary terms, they arrived almost abruptly. Early species, such as Dallosaurus turneri from Texas, still possessed functional limbs capable of supporting the body on land. It likely spent much of its life near coastlines, swimming competently but remaining partly amphibious. Yet, within only a few million years, descendants had transformed into fully marine predators with elongated bodies, paddle-like limbs, and tails adapted for powerful aquatic propulsion. This transition unfolded with unusual speed. Mosasaurs radiated through marine ecosystems so rapidly that by the late Cretaceous, they occupied ecological roles ranging from small shell crushers, scarcely longer than a human being, to gigantic apex predators exceeding 14 meters in length. Few marine reptile groups diversified so extensively within such a compressed span of time. Among the largest was Tylosaurus proriger, preserved within the chalk deposits of the Niobrara Formation in what is now Kansas. Reaching beyond 12 meters long, it possessed a distinctive blunt snout, lacking teeth at the tip. Some researchers propose this structure functioned as a battering ram used to stun prey during high-speed collisions. Fossilized stomach contents reveal a predator with remarkably broad dietary habits. Fish, sharks, marine birds, plesiosaurs, and even other mosasaurs have been identified within the abdominal cavities of different specimens, preserving direct evidence of a highly opportunistic hunter. Their jaws reveal another extraordinary adaptation. Like modern snakes, mosasaurs possessed an intramandibular joint within the lower jaw allowing sections of the jawbone to move independently. This flexibility enabled them to engulf prey items too large to swallow with a rigid bite alone. The feeding strategy differed completely from that of ichthyosaurs or plesiosaurs, whose jaws functioned more conventionally despite their own specialized anatomies. One species, Mosasaurus hoffmanii, holds a special place not only in natural history, but in the history of science itself. Its bones were discovered in a chalk mine near Maastricht in the Netherlands during 1764, long before the concept of extinction had become widely accepted. The enormous jaws sparked fierce debate among scholars and collectors attempting to understand what kind of creature could have produced such remains. The word dinosaur would not exist for another 80 years. What makes the Mosasaur radiation so striking is not merely its speed, but its timing. These reptiles entered oceans already occupied by established marine predators and nonetheless expanded across the globe with remarkable success. Their fossils now appear on every continent, evidence of a lineage that adapted to marine life almost explosively, reshaping itself within a geological moment into one of the final great dynasties of the Mesozoic seas. The plains of western Kansas appear dry beyond imagination now, endless grasslands stretching beneath wind and heat, far from any modern coastline. Yet beneath those fields lies the memory of an inland sea that once divided North America in two. During the Late Cretaceous, from roughly 100 to 66 million years ago, the western interior seaway extended from the Gulf of Mexico to the Arctic Ocean, flooding the center of the continent with warm salt water, shallow enough in many places for sunlight to reach the seafloor. Within its central basin formed the deposits, now called the Niobrara Formation. The water there may have reached depths of only 100 to 200 meters, but it supported one of the most densely populated marine ecosystems of the Mesozoic world. Nutrients circulated continuously through the seaway, sustaining immense populations of fish, plankton, cephalopods, and large predators packed together within relatively confined space. The chalk bluffs preserving this vanished ocean drew fossil hunters during the late 19th and early 20th centuries. Among the most important were Charles Sternberg and his sons, who worked through the Kansas exposures extracting marine reptile skeletons from layers of soft white stone. Their discoveries transformed scientific understanding of Cretaceous oceans. Entire mosasaurs emerged from the chalk with vertebral columns still articulated. Plesiosaurs appeared with elongated necks curving through the rock. Fragile wing bones of flying reptiles remained intact after resting undisturbed for tens of millions of years. The Niobrara fauna carried extraordinary diversity. Mosasaurs moved through the open water alongside long-necked Elasmosaurids and shorter-necked polycotylid plesiosaurs. Giant marine turtles crossed the seaway as well, including Archelanus skyros, the largest turtle ever known, with a shell span approaching 4.6 meters. Massive predatory fish called Xiphactinus reached lengths of around 5 meters, their jaws lined with recurved teeth suited for swallowing prey nearly whole. Above the surface, Pteranodon drifted on broad wings over the water, descending occasionally toward schools of fish breaking near the top of the sea. One fossil from the region captures the violence of this ecosystem with unusual intimacy. Preserved at the Sternberg Museum is a Siphactinus skeleton containing a fully articulated fish nearly 1.8 meters long inside its stomach. The prey, Gillicus arcuatus, appears to have been swallowed whole. Researchers suspect the captured fish thrashed violently enough after ingestion to fatally injure the predator itself. Both animals settled into the sediment together, locked within the same final moment. Food web studies of the Niobrara suggest an ecosystem crowded with apex predators competing across overlapping niches. Multiple large hunters relied upon abundant mid-level prey populations to sustain their size and metabolism. Such systems can appear stable for long intervals while remaining highly sensitive beneath the surface. Declines in forage species or disruptions to plankton productivity ripple upward rapidly when so much biomass depends upon concentrated energy flow through a relatively shallow sea. Even the chalk preserving these fossils records that delicate balance. It formed primarily from the microscopic remains of coccolithophores, tiny algae coated in calcium carbonate plates that drifted continuously through the water column. For millions of years, their remains settled slowly across the seafloor, building vast deposits grain by grain. Within those layers, ancient ocean chemistry, temperature shifts, and biological productivity remain encoded with extraordinary precision, preserving not only skeletons, but the structure of the sea itself. The later Cretaceous seas did not belong to a single mosasaur form. Beneath the surface moved an entire radiation of predators and scavengers, shaped by different diets, hunting styles, and ecological pressures. Each lineage modifying the same ancestral body plan into something increasingly specialized. Within only a few million years, Mosasaurs diversified into one of the most ecologically complex reptile groups the oceans had ever produced. Some developed bodies, suited for open water pursuit, long and narrow with crescent tails driving them through the water column at high speed. Others became thick-skulled crushers of armored prey, carrying jaws built less for slicing flesh than for pulverizing shell and bone. Their differences were not superficial. They represented distinct solutions to surviving within crowded seas already filled with competitors. One of the clearest examples was Globidens dacotensis. Unlike the sharp, conical teeth of fish-hunting mosasaurs, Globidens possessed rounded, almost spherical teeth designed to withstand enormous pressure. Fossilized jaw mechanics suggest an animal adapted for crushing ammonites, clams, and even marine turtles. In some specimens, broken shell fragments remain preserved near the stomach region, direct traces of a feeding strategy entirely unlike the streamlined pursuit predators surrounding it. A similar adaptation evolved independently in Carinodens belgicus, one of the smallest mosasaurs known, measuring roughly 3 meters in length. Found in Maastrichtian deposits of Belgium, it carried compact crushing teeth despite belonging to a separate lineage from Globidens. The repeated emergence of shell-crushing forms within mosasaurs suggests the late Cretaceous oceans offered abundant, hard-shelled prey, enough to support multiple specialists feeding within the same ecological layer. Other mosasaurs moved in the opposite direction, becoming highly efficient pelagic hunters. Platecarpus tympaniticus from the Niobrara Sea possessed a comparatively slender frame and a tail shaped for sustained swimming. For many years, researchers reconstructed mosasaurs with elongated eel-like tails, but soft tissue impressions, described in 2013, revealed something different. Platecarpus carried a bilobed tail fluke resembling that of sharks, indicating propulsion driven primarily by the tail rather than full-body undulation. The discovery altered how scientists imagined mosasaur movement through open water, replacing older images of serpentine motion with something faster and more hydrodynamically refined. Far heavier in build was Prognathodon saturator from the phosphate beds of Morocco. Its skull was broad and deeply reinforced, lined with thick, robust teeth capable of biting into large vertebrate prey. The proportions resemble giant pliosaurs more than the slimmer mosasaurs often reconstructed in earlier decades. In the closing stages of the Cretaceous, forms like Prognathodon occupied the role of heavily armed apex predators within tropical marine environments rich in large prey animals. At the upper edge of mosasaur size stood Hanosaurus bernardi, known from fragmentary remains, in Belgium. Depending on interpretation, some estimates place its length between 12 and 15 meters. The uncertainty surrounding these dimensions reflects the recurring challenge of marine reptile paleontology, where isolated vertebrae or partial skulls must stand in for entire bodies lost to erosion and time. Their fossils now emerge from every continent, including Antarctica, Morocco, Japan, New Zealand, Europe, and the great inland seas of North America, all preserve different pieces of this radiation. What emerges from that global pattern is not repetition, but partitioning. Mosasaurs divided the late Cretaceous oceans with remarkable precision, each lineage adapting toward a narrower ecological role until the seas became populated by an intricate mosaic of specialists moving through the same water under different rules of survival. For more than 150 million years, ichthyosaurs had crossed the oceans in forms ranging from compact coastal hunters to giants rivaling modern whales in mass. Their lineage had endured planetary upheavals, volcanic winters, changing coastlines, and the slow rearrangement of continents. Yet, their disappearance came long before the asteroid impact that would later erase the non-avian dinosaurs and most remaining marine reptiles. By the Cenomanian stage of the late Cretaceous, the decline was already underway. The ocean still contained ichthyosaurs, but the diversity that had once filled Jurassic seas had narrowed dramatically. Where dozens of genera had previously occupied different ecological roles, only a few cosmopolitan survivors remained. The final confirmed representative was Platypterygius, a widespread genus whose fossils appear across nearly every continent before vanishing from the record around 93.9 million years ago. Its disappearance coincided closely with one of the great environmental disruptions of the Mesozoic oceans, the Cenomanian-Turonian Oceanic Anoxic Event, often abbreviated as OAE2. During this interval, oxygen levels in intermediate and deep marine waters fell sharply across much of the globe. Sea levels rose, temperatures increased, and the structure of marine ecosystems destabilized over immense geographic scales. Black organic-rich sediments deposited during this time still preserve the chemical traces of oxygen-starved seas. For predators adapted to active pursuit in open water, such environmental change carried profound consequences. Expanding low oxygen zones compress habitable depth ranges, concentrating prey into narrower ecological bands while simultaneously reducing overall productivity in some marine systems. The disruption extended downward through the food web into the populations of ammonites and other cephalopods that had long formed a substantial part of the ichthyosaur diet. Ammonites themselves suffered major losses during OAE2. Their once extraordinary diversity contracted sharply, removing an important prey base from the ecosystem. In some fossil deposits, the decline appears almost synchronized with the final disappearance of ichthyosaurs. The relationship has led many researchers to view the extinction not as a sudden catastrophe, but as a gradual ecological starvation unfolding over millions of years as prey communities destabilized. Another possibility moves through the same waters. While ichthyosaurs declined, mosasaurs began expanding rapidly across marine ecosystems. Their rise overlaps closely with the final phase of ichthyosaur history, creating the appearance of one predator lineage replacing another. Mosasaurs occupied many similar hunting niches and diversified with remarkable speed during the Late Cretaceous. Some paleontologists argue that increasing competition for prey and habitat may have intensified the pressure already created by environmental instability. The evidence, however, remains incomplete. The fossil record of ichthyosaurs during the final 20 million years of their existence is unexpectedly sparse. Entire stretches of geological time contain only scattered remains, isolated vertebrae, or fragmentary jaws. Oceans preserve fossil evidence unevenly, and absence within the rocks does not always mean absence within the living world. Some species may have persisted longer than current discoveries suggest, inhabiting environments less likely to preserve their remains. Their ending, therefore, appears not as a single dramatic moment, but as a thinning presence across the oceans. A lineage that had once adapted with astonishing speed after the Permian catastrophe slowly receded from marine ecosystems shaped increasingly by different predators, altered chemistry, and changing currents. Long before the final darkness at the end of the Cretaceous, the Ichthyosaurs had already slipped beneath the surface of history. Few structures in the history of vertebrate life appear stranger at first glance than the neck of an Elasmosaurid plesiosaur. In some species, the neck extended so far beyond the body that early paleontologists struggled to imagine how the animal could swim, hunt, or even support such anatomy in moving water. The proportions seem almost dreamlike, as though evolution had briefly ignored ordinary mechanical limits. Among the most extreme examples is Albertonectus vandervelde from Canada. Its neck contained 76 cervical vertebrae, the highest count known in any animal, living or extinct. The structure stretched roughly 7 meters long, while attached to a torso only slightly longer. Vertebra after vertebra formed a continuous articulated column, delicate yet immensely elongated, moving through Cretaceous seas with a geometry unlike anything in modern oceans. For decades, scientists assumed these necks functioned like flexible whips, sweeping laterally through schools of fish while the body remained farther behind. Museum reconstructions often depicted plesiosaurs curling their necks into dramatic loops or swan-like arcs. Yet, advances in imaging technology gradually dismantled that interpretation. CT scans and three-dimensional modeling of vertebral joints revealed that many Elasmosaurid necks possessed surprisingly limited flexibility across their middle sections. A study published in 2017 examined digital reconstructions of these vertebral articulations in detail. The results suggested the neck achieved its greatest mobility near the base and close to the skull, while the long central portion remained comparatively rigid. Rather than functioning as a freely coiling structure, the neck may have operated more like a controlled extension, projecting the head outward from the main body with carefully limited movement. This reinterpretation altered ideas about how these animals hunted. One increasingly supported hypothesis proposes that the elongated neck allowed the small head to approach prey without the disturbance generated by the larger torso behind it. A bulky swimming body pushes pressure waves through water that fish can detect with extraordinary sensitivity. By extending the head far forward on a narrow neck, the plesiosaur may have reduced the warning signals, reaching prey until the final rapid strike. Evidence for plesiosaur locomotion has also been shaped by exceptionally preserved fossils, such as Muranosaurus leedsii from the Jurassic Oxford clay of England. With 44 cervical vertebrae and a beautifully articulated skeleton, it has become central to biomechanical studies, examining how plesiosaurs coordinated their four flippers while stabilizing such elongated necks in open water. Questions remain even at the ocean surface. Some researchers have proposed that long-necked plesiosaurs floated with the body submerged, while the neck rested partially along the surface layer, reducing energetic strain during periods of rest. Such behavior would have exposed the head above water intermittently, though direct evidence remains elusive. The famous legend of the Loch Ness Monster often draws upon these silhouettes, but paleontologists reject the idea of surviving plesiosaurs for reasons extending far beyond the age of the surrounding rocks. Modern understanding of plesiosaur physiology, oxygen demands, reproductive biology, and prey requirements makes survival within a small, cold freshwater loch biologically implausible. These animals belong to expansive marine systems rich in food and oxygen circulation, not isolated inland lakes. Even now, the necks of plesiosaurs remain among the most debated structures in marine reptile science, long chains of bone preserving and engineering problem the oceans carried for millions of years. Not every reptile that entered the ancient seas became a sleek open-water predator. Some carried shells, some remained tied to estuaries and coastlines. Others evolved anatomies so unusual that their relationships remained uncertain for centuries after their fossils were first uncovered. By the late Cretaceous, marine reptile diversity had expanded into a vast mosaic of body plans, feeding strategies, and ecological experiments unfolding simultaneously across the world's oceans. Among the most imposing were the giant marine turtles. Archelon ischiros, recovered from the Niobrara deposits of North America, possessed a carapace stretching roughly 4.6 meters across and may have weighed more than 2,200 kilograms. Its shell differed dramatically from that of modern land tortoises. Rather than a dense, rigid dome, the structure had become lighter and more flexible, reducing drag while retaining support for an enormous body drifting through shallow inland seas. A related form, Protostega gigas, reveals this transition even more clearly. Its skeleton preserves the gradual reduction of heavy shell components that once constrained movement on land. The marine turtle body evolved toward efficiency in water, streamlining the ancient reptilian frame without abandoning the protective architecture inherited from terrestrial ancestors. These animals represented a fully independent experiment in large marine adaptation, separate from Mosasaurs, Plesiosaurs, or Ichthyosaurs. Other reptilian groups occupied the margins between rivers, coastlines, and shallow seas. Certain crocodilian relatives persisted in marine environments long after earlier thalattosuchians had vanished. Teleosauroid forms survived into parts of the Cretaceous, maintaining elongated jaws suited for catching fish near coastal waters. Even enormous semi-aquatic species, such as Sarcosuchus imperator, though not truly oceanic, likely interacted with marine ecosystems where estuaries and river deltas merged into warm, shallow seas. Far earlier in the story, the Gnothosauroids of the Triassic had already begun exploring these same boundaries between land and water. Fossils from the Muschelkalk deposits of Germany and Triassic rocks of China preserve remarkable diversity among these semi-aquatic reptiles. Gnothosaurus mirabilis carried webbed feet and elongated jaws lined with sharp, interlocking teeth, suggesting an ambush hunter feeding on fish within lagoons and coastal channels. These animals would eventually give rise to the pistosauroid lineage from which plesiosaurs emerged. Perhaps the strangest of all were the tanistrophids. In 2020, micro-CT analysis clarified the anatomy of Tanistropheus hydroides, a reptile whose neck exceeded the combined length of its body and tail. For decades, its lifestyle remained controversial because its proportions seemed almost mechanically impossible. The scans revealed a coastal marine predator, adapted for catching fish in shallow water, extending its elongated neck outward while the heavier body remained farther behind. Taken together, these lineages reveal a broader pattern running quietly through the Mesozoic world. At their peak, the seas supported at least 8 separate reptilian groups with marine or semi-marine lifestyles. Some evolved flippers, others shells, elongated necks, crushing jaws, or shark-like tails. The repeated return to the water occurred independently across tens of millions of years, suggesting that the reptilian body possessed extraordinary evolutionary flexibility when exposed to marine opportunity. The oceans kept drawing these animals back. Again and again, terrestrial skeletons reshaped themselves for currents, salt, buoyancy, and open horizons, producing a diversity of forms unmatched by any equivalent reptilian radiation alive today. Sometimes the ancient oceans preserve not merely the bodies of predators, but the final remains of what those predators had swallowed shortly before death. Within fossilized stomach cavities, paleontologists have uncovered fish scales, ammonite hooklets, belemnite guards, fragments of turtle shell, and even the bones of smaller marine reptiles. Each specimen captures a brief interruption in the movement of a living food web, a meal suspended for more than 100 million years inside stone. Among the most common discoveries are the remains of cephalopods, belemnites, squid-like animals carrying internal calcite guards, appear repeatedly within ichthyosaur fossils. One Stenopterygius specimen preserved roughly 1,600 tiny belemnite hooklets clustered together in the abdominal region, traces of tentacles digested long ago while the harder structures remained behind. Such concentrations reveal not occasional feeding, but sustained reliance upon dense cephalopod populations moving through Jurassic seas. Ammonites formed another major component of these ecosystems. Their coiled shells drift through marine sediments across the Mesozoic in astonishing abundance and diversity. They occupied ecological roles somewhat analogous to modern squid and pelagic mollusks, reproducing rapidly and spreading across nearly every marine environment. The rise and fall of ammonite diversity often parallels changes in marine reptile communities with a slight delay, suggesting predator populations expanded or contracted partly in response to fluctuations in this crucial prey base. Teeth preserve another record of diet. Their shape functions almost like an ecological signature, revealing how an animal handled food even when stomach contents are absent. Ichthyosaurs and many mosasaurs carried narrow, conical teeth, ideal for gripping fish and soft-bodied prey. Certain plesiosaurs evolved stronger multi-cusped teeth suited for seizing cephalopods. Shell-crushing forms, such as globidans and the earlier placodonts, developed broad, rounded teeth capable of fracturing armored prey. Some giant pliosaurs and large mosasaurs evolved blade-like serrated teeth adapted for tearing flesh from sizable vertebrates. During the last decade, chemical analysis has added an additional layer to this reconstruction. Carbon and nitrogen isotope ratios preserved within tooth enamel and fossil collagen allow researchers to estimate where animals occupied the food web relative to one another. Between 2011 and 2023, multiple studies applied these techniques to Jurassic and Cretaceous marine ecosystems, reconstructing trophic hierarchies with surprising detail. The results reveal that many marine reptiles sharing the same waters did not compete directly despite apparent similarities. In the Oxford clay deposits of Jurassic England, isotope data indicate that Liopleurodon, Cryptocletus, and contemporary ichthyosaurs occupied distinct feeding niches. Their prey preferences and hunting depths differed enough to reduce direct competition, allowing several large predator lineages to coexist within the same ecosystem simultaneously. Some species appear to have specialized in environments far below the surface. Bone density modifications in Ophthalmosaurus and certain Elasmosaurids suggest repeated deep diving into dim water where sunlight barely penetrated. The prey communities at those depths would have differed substantially from the fish schools and cephalopod swarms inhabiting shallower layers. Marine reptile ecosystems, therefore, extended vertically through the ocean as well as horizontally across geography. Taken together, stomach contents, teeth, chemistry, and bone structure reveal seas organized with remarkable complexity. These reptiles were not simply giant hunters moving randomly through ancient water. They occupied carefully partitioned ecological roles shaped by prey type, depth, swimming style, and metabolism, creating marine food webs as intricate and specialized as those of the modern ocean. Far beneath layers of dark Jurassic shale, one fossil preserves an unusually intimate instant. Inside the body cavity of a stenopterygious mother, several embryos remain curled within the skeleton, while another emerges tail first into water that vanished nearly 180 million years ago. The orientation mirrors the births of modern dolphins, reducing the danger of a newborn inhaling seawater before reaching the surface. Among marine reptiles, this fossil became one of the clearest confirmations that at least some lineages had severed their final dependence upon land. For decades, Mosasaurs occupied a more uncertain place in this story. Their ancestry linked them closely to monitor lizards, animals that still crawl ashore to bury eggs beneath warm soil. Yet evidence recovered from late Cretaceous deposits in Morocco gradually altered that picture. A study published in 2020 described fetal Mosasaur remains associated with a small carinodens-like form, strongly supporting live birth. By the end of the Cretaceous, multiple reptile groups had independently evolved the ability to reproduce entirely at sea, each following a separate evolutionary path toward the same solution. Growth left quieter signatures inside bone itself. Synchrotron scans of Ichthyosaur long bones reveal internal growth rings layered through life like hidden tides. In Stenopterygius, these structures suggest sexual maturity arrived at roughly 10 years of age, with maximum lifespans extending between 25 and 30 years. The pattern resembles the growth tempo of modern bottlenose dolphins more closely than that of living reptiles, another small indication of unusually active metabolisms moving beneath the skin of these animals. Not every skeleton records a peaceful existence. Many preserve scars of survival. Plesiosaur vertebrae sometimes carry deep punctures, matching the spacing of Mosasaur teeth. Ichthyosaur paddles show healed fractures where shattered bone later fused together. Mosasaur remains from late Cretaceous seas occasionally bear shark bite marks, traces of encounters that did not immediately prove fatal. Fossils transform injury into permanence, preserving moments of violence alongside evidence that some individuals endured long after trauma. Disease also reached these oceans. One Jurassic Ichthyosaur specimen preserves bone heavily remodeled by osteomyelitis, a bacterial infection that slowly consumes living tissue. The swollen, irregular texture of the affected bone indicates the animal survived for an extended period while the infection progressed. It stands among the oldest confirmed examples of this disease in the vertebrate fossil record, a reminder that even in vanished ecosystems, bodies remained vulnerable to microscopic forces invisible within the water around them. The question of reproduction continues to linger most strongly around plesiosaurs. No nesting grounds have ever been discovered, and their broad hydrofoil limbs appear poorly suited for hauling heavy bodies onto shore in the manner of modern sea turtles. Some researchers propose they too gave birth in open water, though direct fossil evidence remains elusive. A remarkable specimen named Polycotylus, preserved with a single large embryo, strengthened this possibility, hinting that at least certain plesiosaurs carried well-developed young internally rather than producing large clutches of eggs. Juvenile fossils remain unexpectedly scarce across many marine reptile groups. Tiny skeletons are far rarer than adult remains, despite the likelihood that countless young animals once filled coastal nurseries and shallow seas. Perhaps fragile juvenile bones simply vanished before burial. Perhaps the youngest individuals occupied environments less likely to fossilize. Their absence leaves quiet gaps within the record, spaces where entire early lives drift beyond the reach of stone. Long before laboratories filled with scanners and digital reconstructions, the ancient seas emerged slowly from damp cliffs and shattered stone in small coastal towns where storms carried fossils into daylight. Along the shoreline of Lyme Regis in southern England, winter landslides exposed dark Jurassic layers rich with creatures no living person had ever seen. There, in 1811, a 12-year-old girl named Mary Anning uncovered the skull of what became the first correctly identified Ichthyosaur. The animal seemed almost impossible at the time, a reptile shaped for water rather than land, with jaws full of conical teeth and enormous eye sockets staring from the rock. Anning continued searching the unstable cliffs for decades, often working in dangerous conditions after heavy rain loosened the hillsides above the beach. In 1823, she uncovered the first complete Plesiosaurus. Its neck stretched through the stone in a pattern unlike any known animal. 5 years later came Dimorphodon macronix, a flying reptile from the same coast. Wealthy collectors and gentlemen geologists purchased many of her discoveries, then published scientific descriptions that frequently omitted her name. The fossils traveled into museums and private collections, while the woman who found them remained largely outside the scientific institutions built around them. William Conybeare and Henry de la Beche belonged to that world of educated Victorian geology. Conybeare formally described and named Plesiosaurus in 1821, using material largely recovered by Anning herself. Though he later acknowledged her importance more openly than many contemporaries, the imbalance remained visible throughout the early history of paleontology. The fossils of ancient oceans passed through many hands before entering scientific literature, and the names attached to discoveries often reflected social class as much as scientific contribution. Across the Atlantic, a different atmosphere shaped the next phase of marine reptile discovery. During the 1870s and 1880s, Edward Drinker Cope and Othniel Charles Marsh competed with obsessive intensity in what became known as the Bone Wars. Their rivalry spread across the fossil beds of North America, including the chalk deposits of Kansas, where Mosasaurs and Plesiosaurs rested beneath former Cretaceous seas. Expeditions raced to collect specimens before competitors arrived. New species were named in rapid succession. Important discoveries emerged beside duplicated names, damaged fossils, and hurried descriptions shaped by personal hostility as much as scientific curiosity. Among the researchers connected to this era, Samuel Wendell Williston brought unusual precision. His studies of Niobrara mosasaurs and fossil fish established anatomical standards that later paleontologists continued to rely upon long after the Bone Wars faded into history. Careful comparison gradually replaced competitive excess, and marine reptile science matured into something steadier and more methodical. New centers of discovery later appeared far from England and Kansas. Since the 1990s, the phosphate mines of Morocco have produced an astonishing abundance of late Cretaceous marine reptile material. Researchers, including Nizar Ibrahim, helped reveal ecosystems crowded with mosasaurs of many forms, from shell crushers to apex predators. New species continue to emerge from sediments deposited near the very end of the age of reptiles. Even now, many discoveries still begin with ordinary people walking exposed shorelines after storms. Amateur collectors along the Jurassic coast and the chalk deposits of Belgium continue to recover specimens that reshape scientific understanding. Modern technology has transformed what follows. Micro-CT scanning and digital preparation now allow researchers to examine delicate internal structures without cutting into the fossils themselves. Brain cases, inner ears, and hidden skeletal details appear gradually on computer screens, as though the stone has learned, after millions of years, how to speak softly from within. Inside certain marine reptile skulls, the rock preserves more than bone. Empty spaces once occupied by delicate brain tissue hardened into natural molds over millions of years, leaving behind faint internal contours that modern scanners can now trace in 3 dimensions. These digital endocasts do not reveal thoughts or memories, yet they offer subtle outlines of perception itself, the proportions of optic lobes, cerebellums, and sensory pathways arranged within animals that vanished before flowering plants spread widely across Earth. Among ichthyosaurs, the most striking feature is often connected to vision. Their endocasts show unusually enlarged optic lobes, matching the enormous eyes already visible in many skulls. In species such as Ophthalmosaurus, the eyes grew to astonishing proportions, capable of gathering dim light from deep water where sunlight weakened into blue darkness. The brain regions associated with visual processing expanded accordingly, suggesting hunters guided primarily by sight, somewhat comparable in sensory emphasis to modern billfish and other visually oriented marine predators moving through open water at speed. Mosasaur brains preserve a different emphasis. Digital reconstructions from species including Platecarpus and Tylosaurus reveal relatively large cerebellums, regions associated in living animals with coordination, balance, and proprioception. The constant internal awareness of body movement through space. Their long, muscular bodies and powerful tails required precise control during pursuit and rapid turns beneath the water. Though separated from modern monitor lizards by tens of millions of years, the neurological foundations of that ancestry still linger faintly within the proportions of the skull. Chemical sensing may also have shaped their experience of the ocean. As close relatives of varanid lizards and snakes, mosasaurs likely possessed a vomeronasal system, often called Jacobson's organ, capable of processing chemical particles collected by the tongue. In living monitor lizards, the tongue flickers constantly through the air, carrying invisible traces toward sensory chambers in the roof of the mouth. Something similar may once have operated beneath Cretaceous seas, allowing mosasaurs to follow prey trails through water rich with dissolved chemical signals. Ichthyosaurs and plesiosaurs appear to have lacked this system entirely, revealing how separate evolutionary histories produced different sensory worlds within the same oceans. Sound moved differently through those ancient waters as well. In ichthyosaurs, the dense structure of the stapes, the hearing bone linking inner structures of the skull, suggests sensitivity to low-frequency vibrations, traveling long distances underwater. The mechanism differed anatomically from that of whales, yet both lineages face the same physical reality of sound transmission through dense fluid. Oceans carry vibration farther than air, and these reptiles likely inhabited an acoustic landscape filled with distant movements beyond immediate sight. Behavior leaves far more uncertain traces. At certain fossil sites, multiple Shonosaurus individuals lie together in dense accumulations, hinting at possible aggregating behavior. Some juvenile ichthyosaurs have also been found near adults, suggesting at least temporary group association. Whether these gatherings reflected migration, mating, feeding, or simple environmental catastrophe remains unresolved. Stone preserves position more easily than intention. Beyond these fragments, the curtain closes quickly. No fossil can fully reveal the texture of movement through living water, the color shifts across skin in changing light, or the sounds exchanged between animals crossing open seas. Their navigational instincts, social structures, and cognitive lives remain largely inaccessible. Even with modern imaging technology, much of their existence survives only as partial outlines, suspended between evidence and silence inside the patient memory of rock. The final chapter of the Cretaceous Ocean did not begin with sudden violence. Long before the asteroid arrived, coastlines had already started to withdraw from the continents like a slow exhalation. Across North America, the vast western interior seaway narrowed gradually as the rising Rocky Mountains altered the shape of the land itself. Warm, shallow water that had once stretched from the Gulf of Mexico to the Arctic retreated into shrinking basins and disconnected coastal corridors. Habitats that had supported generations of marine reptiles compressed over millions of years into smaller and less stable environments. Within those changing seas, the ammonites were also fading. Their coiled shells still drifted through late Cretaceous waters in enormous numbers, yet their diversity had diminished substantially from the flourishing complexity of the mid-Cretaceous. Earlier oceans had contained hundreds of ammonite genera, occupying many ecological roles, but by the Maastrichtian, only a few dozen major lineages remained. Some forms grew elaborate ridges and spirals, as though ornamentation intensified, while the broader family quietly narrowed around them. Since ammonites formed a major prey source for many marine predators, their decline may have carried consequences upward through the food web long before the boundary event itself arrived. The Mosasaurs present a more difficult picture. Fossils from the latest Cretaceous still reveal impressive diversity, with giant hunters sharing the seas beside shell crushers, deep-water specialists, and smaller coastal species. Certain analyses suggest overall richness remained stable, perhaps even increasing toward the end. Other studies detect regional declines and narrowing geographic ranges during the final million years of the Cretaceous. The disagreement emerges partly from the uneven fossil record itself, where some coastlines preserve abundant remains while others vanish entirely from geological memory. A study published in 2021 examined these late Mosasaur distributions and found evidence that several lineages experienced range contractions during the Maastrichtian. Cooling sea temperatures may have contributed to this pattern, especially near the poles and within certain inland seas. Far away in what is now India, the Deccan traps had begun erupting approximately 300,000 years before the Chicxulub impact. Layer after layer of basalt flooded across the landscape through immense volcanic episodes, releasing vast quantities of carbon dioxide and sulfur dioxide into the atmosphere. These eruptions continued even after the asteroid impact itself, altering climate across intervals measured not in days, but in geological pulses. The oceans responded slowly to such disturbances. Periods of warming may have alternated with volcanic cooling caused by sulfur aerosols drifting high through the atmosphere. Ocean chemistry shifted repeatedly. Acidification affected organisms dependent upon calcium carbonate shells, including many planktonic species, forming the foundation of marine ecosystems. Some researchers interpret these changes as evidence that marine life already endured physiological stress before the asteroid arrived. Others argue the fossil record shows no decisive signal of widespread ecological collapse before the boundary, only ordinary fluctuations within a dynamic world. Among plesiosaurs, the latest evidence appears comparatively stable. Elasmosaurids and polycotyllids remained widespread during the Maastrichtian, inhabiting seas across multiple continents without a clear sign of prolonged decline. Their disappearance, therefore, appears more abrupt in many analyses, less like a slow fading and more like a sudden extinguishing. By the final few 100,000 years of the Cretaceous, the oceans still held giant reptiles, ammonites, sharks, turtles, and vast schools of fish moving through productive water beneath familiar stars. Yet, beneath that apparent continuity, coastlines shifted, climates oscillated, and ancient ecosystems tightened quietly around pressures accumulating far below the threshold of immediate perception. Far above the warm seas of the late Maastrichtian, a body between 10 and 15 kilometers wide crossed the inner solar system on a collision path that had already become irreversible long before Earth existed. Approximately 66.043 million years ago, it struck the shallow carbonate platform of what is now the Yucatan Peninsula at nearly 20 kilometers per second. The impact lasted only moments. Yet, within those moments, an oceanic world, more than 180 million years old, began to unravel. The collision excavated an immense crater and vaporized roughly 100,000 cubic kilometers of rock almost instantly. Limestone and sulfate-rich sediments transformed into incandescent gas and debris hurled high into the atmosphere. Soot from global wildfires soon joined the expanding cloud. Within days, the upper atmosphere carried a dense veil of sulfate, aerosols, and fine particles that spread around the planet, reducing sunlight, reaching the ocean surface to a faint and temporary twilight. Marine ecosystems depended upon that light more completely than the giant reptiles hunting within them. Across the surface waters, phytoplankton drifted invisibly in immense numbers, converting sunlight into the energy supporting nearly every marine food chain. As darkness settled across the oceans, photosynthesis collapsed. Productivity fell rapidly within weeks. Zooplankton populations declined soon afterward, followed by fish, cephalopods, and larger predators. The extinction moved upward through the ecosystem like a slow withdrawing tide, starving the living structure of the sea from its very base. The chemistry of the water changed as well. Sulfate compounds released by the impact dissolved into rainfall and surface oceans as sulfuric acid, intensifying acidification already linked in part to the Deccan eruptions before the impact. Organisms dependent upon calcium carbonate shells faced severe disruption. Among the most vulnerable were the ammonites, whose long evolutionary history ended with startling abruptness at the boundary itself. Their coiled shells vanished from the fossil record almost immediately afterward, erasing one of the defining lineages of the Mesozoic ocean. Closer to the impact site, the sea responded with overwhelming physical force. Modeling studies suggest the collision generated tsunamis of extraordinary scale, radiating outward through the Proto-Atlantic and Gulf of Mexico. Coastlines, thousands of kilometers away would have experienced violent inundation within hours. Sediment layers from multiple regions preserve chaotic deposits linked to these waves, where marine and terrestrial material became mixed together in sudden turbulent burial. The atmosphere itself briefly became a source of heat. Material blasted upward from the crater eventually re-entered the atmosphere across the globe, converting kinetic energy into thermal radiation. Forests ignited over immense areas of land. The uppermost ocean layers likely experienced intense but temporary heating before longer-term cooling followed beneath the darkened skies. The sequence produced a world oscillating between extremes, heat and darkness, fire and cold, all unfolding over intervals too rapid for large ecosystems to adapt. For the last mosasaurs, plesiosaurs, and giant sea turtles, survival became increasingly difficult in the months after the impact. Surface waters cooled sharply as sunlight disappeared. Prey populations diminished across nearly every trophic level. Acidification altered the chemistry of shallow seas, while the collapse of photosynthesis deprived the ocean of its normal biological rhythm. These animals had endured volcanic crises, climatic shifts, shrinking coastlines, and changing seas across millions of years. Yet the post-impact ocean represented something fundamentally different, a planetary disruption arriving faster than evolutionary change could answer, until the great reptilian presence in the oceans finally passed into stone and silence. Thin currents still moved through the oceans after the darkness began to lift. Sunlight gradually returned to the surface waters, touching coastlines where fragments of older ecosystems persisted in diminished and altered forms. The age of marine reptiles had ended, yet the sea itself had not fallen silent. Smaller bodies continued to drift beneath the recovering light, carrying within them certain traits that catastrophe had not entirely erased. Among the survivors were many sharks and numerous lineages of bony fish, along with sea turtles and several crocodilian groups inhabiting rivers, estuaries, and coastal margins. At the foundation of the food web, enough microscopic organisms endured to begin rebuilding marine productivity over long spans of time. The pattern was uneven and selective. Entire dynasties vanished forever, while other animals crossed the boundary with surprising persistence. The contrast between sea turtles and mosasaurs became one of the clearest lessons preserved within the extinction itself. Both belonged to the reptilian world of the late Cretaceous seas. Both breathed air. Both occupied oceans, collapsing under acidification, darkness, and food scarcity. Yet the giant mosasaurs disappeared completely, while sea turtles endured and continued into the modern age almost without interruption. Part of the explanation may have rested in metabolism. Sea turtles, being ectothermic, required far less energy than the enormous predators that had dominated the upper layers of the food chain. In periods of prolonged scarcity, a slower metabolism becomes less a limitation than a shield. Some turtles could likely reduce activity for extended intervals, surviving on diminished resources while ocean ecosystems struggled to recover. Their diets also offered flexibility. Marine turtles fed upon jellyfish, algae, mollusks, and other lower trophic-level organisms that recovered more quickly than the large vertebrate prey hunted by mosasaurs. Body size shaped the outcome as well. Across multiple extinction events in marine environments, larger tetrapods repeatedly faced greater risk of disappearance. A 12-meter mosasaur required a constant flow of abundant prey simply to sustain its movement through the sea. When primary productivity collapsed after the impact winter, the energetic mathematics of such an existence became impossible. Smaller animals, needing less food and reproducing more rapidly, possessed a narrow but critical advantage during the ecological famine that followed the impact. The extraordinary specialization of mosasaurs may also have deepened their vulnerability. During the stable final stages of the Cretaceous, they had diversified into shell crushers, pursuit hunters, apex predators, and mid-sized generalists occupying distinct ecological niches across nearly every ocean basin. Yet this sophistication depended upon a functioning pyramid of marine productivity beneath them. Once the lower structure failed, the upper layers lost stability with remarkable speed. Adaptations that once sharpened efficiency became constraints in a radically altered world. Crocodilian survivors reveal another asymmetry within the extinction. Freshwater rivers and lakes suffered severe disruption, yet they were partly insulated from the total collapse experienced in the open ocean. Detritus-based food webs and terrestrial nutrient input continued supporting some aquatic ecosystems even while marine phytoplankton productivity crashed. Coastal and freshwater crocodilians therefore occupied environments buffered from the full force of oceanic starvation. What remained afterward was a quieter rule written across deep time. Ecological dominance and long-term resilience are not the same condition. The animals most perfectly shaped for a stable world often stand nearest the edge when that stability disappears. For a long interval after the boundary clay settled across the world, the oceans carried an unfamiliar emptiness. The giant hunters were gone. No mosasaur shadows crossed the continental shelves. No long necks drifted beneath the dim surface currents. In the earliest Paleocene seas, food webs had been stripped back to simpler forms, their complexity reduced almost to a skeletal outline. Phytoplankton communities slowly recovered beneath clearer skies, rebuilding the invisible foundation upon which all larger marine life depended. Yet for hundreds of thousands of years, the upper ocean remained strangely vacant of large vertebrate predators. Into that quieter world came mammals, still tethered to the land. Around 53 million years ago, in river systems bordering the ancient Tethys Sea, a small hoofed predator known as Placodont moved through shallow water along the margins of what is now Pakistan. It was not yet a whale in any recognizable sense. Its limbs still carried its weight on land, and its spine belonged to a running animal rather than a swimmer. Yet within roughly 15 million years, descendants of those shoreline mammals would become fully oceanic, producing archaeocetes capable of crossing open seas with bodies reshaped entirely by water. The transition succeeded partly because mammals already possessed certain biological tools that marine reptiles had reached only unevenly or through separate evolutionary pathways. Endothermy was deeply established, allowing stable internal temperatures in colder oceans and sustained activity over long distances. Live birth was also already intrinsic to mammalian biology, removing the reproductive constraints faced by many reptiles returning to marine life. In the aftermath of the extinction, there were no giant reptilian competitors left to slow this expansion into the vacant pelagic realm. Marine reptiles did survive into the modern world, though only in narrower forms. Sea turtles continued moving between coastlines and nesting beaches. Sea snakes emerged during the Eocene, around 40 million years ago, becoming elegant specialists of warm, shallow waters. Saltwater crocodiles retained an amphibious existence between rivers, estuaries, and coastal margins. Marine iguanas later grazed algae along volcanic shores in the Pacific. None expanded into the immense ecological breadth once occupied by ichthyosaurs, plesiosaurs, or mosasaurs. Part of the reason lies in the arrival of cetaceans themselves. As whales diversified Through the Eocene and Oligocene, they expanded into nearly every large marine predator role available in the open ocean. Some became pursuit hunters, others deep divers, filter feeders, ambush predators, or long-distance migrators crossing entire hemispheres. Their physiology granted advantages difficult for reptiles to match. High metabolic output sustained powerful swimming muscles and enlarged brains, while complex social learning allowed behaviors to spread culturally through populations rather than solely through genetic inheritance. Across geological time, this became an immense example of competitive exclusion. Once cetaceans established themselves within the major pelagic niches, the ecological space once occupied by giant marine reptiles effectively closed behind them. A large marine reptile lineage, evolving afterward, would not have entered an empty ocean, but one already dominated by warm-blooded mammals, adapted to nearly every layer of the sea. Some paleontologists have wondered whether this outcome might eventually have unfolded even without the asteroid impact. Certain marine reptile groups had already shown hints of elevated metabolism, while mammals on land were diversifying steadily. The oceans may have been moving gradually toward a world favoring endothermic vertebrates long before the final catastrophe arrived. There are moments in paleontology when absence becomes more important than discovery. Certain layers of stone seem to hold their silence with unusual determination, preserving fragments of entire worlds while withholding the precise transitions that would explain them. Along the shorelines of the early Triassic, where the first marine reptiles entered the recovering seas, this silence remains especially deep. The origin of ichthyosaurs stands at the center of that uncertainty. Their transformation from land-dwelling reptiles into fully oceanic swimmers appears in the fossil record with startling speed. Within only a few million years, they possessed streamlined bodies, powerful tails, enlarged eyes, and limbs reshaped into flippers. Yet the intermediate stages remain elusive. The rocks preserving shallow coastal environments from that interval are sparse in many regions, and the animals themselves may have occupied habitats poorly suited for fossilization. What survives instead is the impression of an evolutionary leap whose earliest steps still lie hidden. Other puzzles drift upward from younger sediments. In South America and Antarctica, fossils of Aristonectes and certain related polycotyllids have been recovered from deposits interpreted as freshwater or brackish environments. These discoveries suggest that at least some plesiosaurs may have tolerated wide salinity ranges, moving between marine and river-influenced systems in ways once considered unlikely for fully pelagic reptiles. Their bodies, long associated almost entirely with open seas, now hint at ecological flexibility still not fully understood. Meanwhile, the phosphates of Morocco continue yielding mosasaurs at a remarkable pace. Since the early 2000s, new species have emerged from the mines almost yearly, revealing an end Cretaceous fauna far more diverse than earlier reconstructions suggested. Some possessed crushing dentition, others narrow pursuit skulls, and others immense jaws suited for large vertebrate prey. Piece by piece, the southern margin of the ancient Atlantic is being rebuilt from bone beds still only partially explored. The chemistry locked inside fossils has begun opening another frontier. Ancient DNA has not survived in marine reptile remains, the immense span of time rendering it unstable beyond recovery. Yet, in 2018, researchers extracted fragments of collagen from a 180-million-year-old ichthyosaur. Protein molecules endure longer than DNA, and their survival raised the possibility that future sequencing techniques may eventually recover deeper biochemical traces of extinct animals than once imagined possible. Large regions of the former Tethys coastline also remain understudied, Marine reptile material is known from Pakistan, the Middle East, and the uplifted rocks of Himalayan Tibet, yet political instability, difficult terrain, and logistical barriers have slowed sustained fieldwork. Entire faunas may still rest within formations rarely visited by vertebrate paleontologists. Even the colors of these animals remain uncertain. Evidence for countershading in ichthyosaurs suggested dark backs and pale undersides, similar to many modern marine hunters, but the study has not yet been widely replicated across other groups. Whether some species carried stripes, mottling, or more complex patterns remains unknown. Inside museum drawers and unopened plaster jackets, another hidden ocean still waits. Machine learning systems are beginning to assist with CT analysis and digital preparation, revealing bones concealed inside stone without damaging them. Some researchers suspect that undescribed marine reptile specimens already exceed the number of formally named species. The ancient seas may therefore remain only partially visible, their full shape still emerging slowly from the rock. Across the surface of the modern sea, old rolls continue beneath new skins. Dolphins arc through schools of fish with the same streamlined precision once carried by ichthyosaurs. Killer whales move as apex hunters through cold water ecosystems once ruled by Pliosaurs and Mosasaurs. Sea lions pursue shoaling prey along continental margins where marine reptiles once hunted among ammonites and belemnites. The ancient actors vanished, yet the ecological positions they occupied remained, waiting for other lineages to inherit them. This continuity is one of the clearest demonstrations of convergent evolution ever uncovered in the fossil record. The resemblance between ichthyosaurs and dolphins reaches far beyond general outline. Detailed hydrodynamic studies show remarkably similar solutions to movement through dense fluid environments. Both evolved fusiform bodies that minimize drag, crescent-shaped tail structures optimized for sustained swimming efficiency, and sensory systems centered heavily upon vision and rapid prey tracking. Even the distribution of mass through the body converged toward comparable balances of stability and acceleration. Separated by roughly 180 million years and descending from entirely different branches of vertebrate life, they nevertheless approached the same physical answer to the demands of open ocean pursuit. Not every ancient role returned so cleanly. Ammonites, among the most abundant and varied animals of the Mesozoic seas, vanished completely at the end of the Cretaceous. Over more than 300 million years, they produced upward of 10,000 species, filling oceans with spiraled shells that drifted through nearly every marine habitat imaginable. Their extinction removed not merely a lineage, but an entire style of life. Modern squid and nautiluses preserve faint echoes of that vanished world, yet no surviving group occupies the precise ecological breadth ammonites once held. The great predators of the present ocean now stand within systems carrying familiar vulnerabilities. Killer whales, sperm whales, and large predatory sharks occupy positions comparable in ecological dominance to the marine reptiles of earlier eras. Their survival depends upon complex food webs extending downward into plankton blooms, nutrient cycles, and stable ocean chemistry. When those foundations shift, even the most powerful hunters become exposed. In some regions, modern oceans are already developing, expanding zones of depleted oxygen. The Cenomanian-Turonian anoxic event that coincided with the disappearance of the ichthyosaurs has distant parallels in these growing dead zones, though driven today by warming waters and nutrient runoff from human activity. Layers of poorly oxygenated water spread outward through coastal seas, altering migration routes and compressing habitable depth ranges for many organisms. The past no longer feels entirely remote when viewed through this lens. It becomes a record of system behavior under stress. Ocean acidification carries another echo. At the end of the Cretaceous, rapid chemical disruption devastated calcifying organisms dependent upon stable carbonate conditions. In the modern ocean, rising atmospheric carbon dioxide dissolves into seawater and shifts its chemistry once again. Pteropods, corals, and shell-forming mollusks already show measurable dissolution effects across surprisingly short timescales, their structures weakening molecule by molecule beneath increasingly acidic water. Taken together, the long history of marine reptiles reveals an ocean that is neither fixed nor guaranteed. Over 180 million years, entire dynasties rose, diversified, and disappeared, while the sea continuously reorganized itself around changing climates, chemistries, and extinctions. Stability in the ocean has always been temporary, even during intervals that seemed immeasurably vast from within them. Long before human beings stood beside oceans and gave names to whales or sharks, other vertebrates had already mastered those waters for spans of time almost impossible to hold in the mind. Ichthyosaurs alone endured for roughly 157 million years, more than twice the interval separating the present day from the extinction of the non-avian dinosaurs. Their story was not brief, nor fragile, nor unsuccessful. By every evolutionary measure available, they belonged among the great triumphs of vertebrate history. It is only from the far shore of extinction that their world appears temporary. Knowing the ending alters the shape of everything before it. Yet inside the Jurassic Ocean, there would have been no signal that these animals were living in a fading age. Plesiosaurs crossed entire seas beneath storms and moonlit tides. Ichthyosaurs pursued belemnites through open water with bodies refined by millions of years of selection. Mosasaurs later rose into ecosystems already ancient, filling predator niches with astonishing speed and precision. Nothing in those oceans suggested inevitability. The seas belonged to them as completely as modern oceans belong to whales today. Again and again, across the Mesozoic, evolution returned reptiles to the water. Some lineages became streamlined, pursuit hunters, others shell crushers, ambush predators, coastal stalkers, or deep-diving specialists. The pattern repeated so many times that it begins to feel almost musical. Evolution does not move with foresight or intention, yet similar environments repeatedly drew distant branches of life toward similar solutions. The ocean kept calling land animals back into itself, reshaping bone and muscle into forms capable of moving through immense blue distances. Their diversity also unsettles the idea that ecosystems possess a fixed or natural state. An ocean filled with mosasaurs was no less real or balanced than one filled with sperm whales. Both worlds emerged from the same physical constraints of fluid motion, prey distribution, metabolism, and chemistry. Different lineages simply arrived at different answers. What feels permanent in one age becomes unimaginable in another. Human beings often inherit the illusion that the living world surrounding them is the baseline from which all change is measured. Yet the geological record dissolves that assumption layer by layer. The modern ocean, with its dolphins, seals, tuna, and whales, is only the current arrangement within a system that has reorganized itself repeatedly across deep time. Entire dynasties once vanished from seas that afterward appeared ordinary again beneath new skies. Still, beyond the abstractions of extinction curves and evolutionary theory, The animals themselves deserve a final stillness. Giant ichthyosaurs once turned slowly beneath sunlight, filtering through Triassic water. Plesiosaurs moved with four wing-like flippers through cold green depths. Mosasaurs patrolled the broad interior sea that once covered the center of North America, where wheat fields now move in the wind across Kansas. They were not myths, assembled backward from scattered bone. They were living creatures with territories, injuries, hunts, births, and deaths extending across millions of years. This entire understanding rests upon a distinctly human act of attention. A child walking the Dorset coast in 1811 looked into fractured stone and recognized the shape of something ancient and alive. Since then, countless collectors, preparators, divers, quarry workers, and researchers have continued that same quiet labor, lifting forgotten oceans back into the light one fossil at a time. A human life passes so quickly that even history can feel immense. Yet geological time quietly exceeds the scale of ordinary intuition. 66 million years sounds like an abstraction until it is translated into smaller motions of thought. If 1 second represented 1,000 years, the extinction at the end of the Cretaceous would have happened only 18.4 hours ago. The first ichthyosaurs would have entered the oceans around 70 hours ago. The formation of Earth itself would rest just 4.6 years behind the present moment, still close enough to imagine on a calendar hanging beside a door. Everything described in this long-vanished oceanic world survives because of accidents so improbable that they border on silence. An animal died in precisely the right place. Oxygen remained scarce enough to slow decay. Sediment arrived gently. Then pressure accumulated across millions of years until flesh vanished and minerals settled into its shape. Most living things disappear without leaving any trace at all. The fossil record is built almost entirely from exceptions, scattered survivals preserved against overwhelming odds. And yet, those survivals carry astonishing amounts of information. A vertebra lifted from Jurassic shale can reveal growth rate through microscopic rings hidden inside bone. Tooth wear can suggest diet. Stable isotopes preserve echoes of ancient food webs and water temperatures. Pigment-bearing structures inside fossil skin can hint at color patterns that vanished before mammals had meaningfully diversified. A human hand can hold the mineralized remains of a creature 180 million years old and still recover fragments of its biology with methods grounded in chemistry and physics. Familiarity risks making this seem ordinary, though it never truly is. Deep time alters perspective in subtler ways as well. Once the mind genuinely settles into spans measured in tens of millions of years, permanence becomes difficult to imagine anywhere. Continents rearrange themselves. Oceans appear and vanish. Dominant groups fade. Entire ecosystems survive only as thin layers in stone. This does not empty the present of meaning. If anything, it sharpens it. Temporary things become more vivid when understood clearly as temporary. The strange strength of paleontology lies in how rigorously it extracts knowledge from absence. No person will ever watch an ichthyosaur swim beneath Triassic sunlight. No recording preserves the motion of a mosasaur turning through the chalk sea. Everything known about them emerges from inference, disciplined by evidence. Bone articulations constrain movement. Hydrodynamics constrain body shape. Comparative anatomy limits speculation. Chemistry narrows possibility further still. The resulting picture is incomplete. But incompleteness is not the same as ignorance. Science moves carefully through uncertainty, removing impossibilities until a smaller and more coherent reality remains. Even now, the story continues to expand beyond what is currently understood. Somewhere, perhaps in a coastal cliff or beneath desert sediment, a fossil is slowly emerging from rock, while no human yet knows it exists. A new specimen may alter the timeline of an extinction, reveal a color pattern never before seen, or expose an anatomical feature that rearranges an entire branch of the reptile family tree. The stone has not finished speaking. There is also something distinctly human in the ability to care about creatures that no longer exist anywhere on Earth. To look at a fossil and recognize not merely age, but absence, requires a peculiar form of imagination. The mind reaches backward across impossible spans of time and briefly restores a vanished life to motion before letting it drift quietly into the dark again. Along the Dorset coast, winter rain still loosens stone from the cliffs exactly as it did when Mary Anning walked beneath them carrying a hammer and wicker basket. The sea continues its patient work there, grain by grain, tide by tide, opening fractures in shale that have remained sealed since the Jurassic. Somewhere inside those collapsing walls are vertebrae that have never seen daylight, the outline of a paddle still pressed into mud older than birds, perhaps the skull of an animal no human has yet imagined. The cliffs endure as a moving boundary between present time and a world so ancient that none of the creatures alive today would have recognized it. The ground itself has become a kind of archive written in bodies. Chalk beneath the English Channel is composed largely of microscopic shells that drifted downward through warm Cretaceous water for millions of years. The phosphate beds of Morocco contain fragments of Mosasaurs, fish, sharks, and turtles packed together in dense mineral seams. Beneath the plains of Kansas, the Niobrara limestone still holds the remains of an inland sea crowded with predators. The animals of those vanished oceans did not simply disappear. Their bones entered the chemistry of continents. Their shells became sediment. Their deaths accumulated slowly into landscape. The modern ocean carries different shapes now, yet the physical system itself remains recognizably the same ocean that rolled above plesiosaurs and ammonites. Currents still circulate heat between hemispheres. Nutrients still rise from darkness toward sunlight. Carbon still dissolves into seawater and alters its chemistry molecule by molecule. Measurements taken across recent decades show that average ocean surface temperatures have risen by approximately 3.8 degrees Celsius over the last 50 years. Acidity has increased measurably. Oxygen minimum zones continue expanding through parts of the open sea. These are not prophecies suspended somewhere in the future. They are observations already present in the water. The geological record preserves earlier moments when oceans changed too quickly for many species to adapt. The end Permian extinction unfolded beneath severe warming and oxygen loss. The end Triassic brought volcanic disruption and ecological turnover. During the Cenomanian-Turonian anoxic event, marine ecosystems reorganized under spreading low oxygen waters. The end Cretaceous combined darkness, acidification, collapse of primary productivity, and abrupt climatic instability into a single devastating interval. Each crisis differed in cause and pace, yet all reveal the same underlying truth. Marine ecosystems are resilient across ordinary time, but under sufficient stress they can reorganize completely. What the marine reptiles leave behind is not quite a warning and not quite consolation. It is something steadier than either. Ichthyosaurs crossed the oceans for over 150 million years. Plesiosaurs evolved forms stranger than myth. Mosasaurs inherited entire seas and filled them with astonishing diversity. Their dominance must once have seemed as permanent as tides themselves. Then conditions changed, and the balance that sustained them dissolved. Somewhere in the rocks there exists a final Mosasaur individual, the last representative of a lineage that had ruled the late Cretaceous ocean. It swam through water, already changing beyond recognition, hunted prey, growing scarcer, died, and left no descendants. The sea closed over that moment without ceremony and continued moving above the sinking body. Tonight, it still moves. Water once lifted into Jurassic storms now travels through modern currents and clouds. Molecules that drifted above the Tethys may fall again as rain across fields or cities. The past has never truly vanished. It circulates quietly through stone, salt, atmosphere, and memory, returning again and again in altered forms beneath the turning light of the same enduring sun.